There are many data types in computing, but one of the most common are stacks. They're used almost everywhere, often even without even realizing. Fortunately, they're also one of the most basic, which makes them a great choice for this new series on data structures. As always, I've got my simple macOS project here, a terminal project to work with, and we're going to write out the code for a stack in here. But first, I want to conceptually explain to you what stacks are, in case you haven't seen them before. If you've ever been to a carnival or a fun fair and played a hoopla game, you'll know the goal is to throw hoops onto a pole. And ideally, if you're good, the hoop goes over the pole, falls down to the bottom, and hurrah, you've got a point. And if you do that 3 times, or maybe even 5 times perhaps, then you win some terrible prize, like a little teddy bear or something, right? And these hoops stack up, 1 hoop, 2 hoops, 3 hoops, like that. And if you think about it, if you want to remove the bottom hoop, you have to but first remove the second hoop. And if you want to remove the second hoop, you got to first remove the third hoop. So the third one comes out, then the second one, then the first one. And in computing science, we call this LIFO, for last in, first out. So if you imagine, 1, 2, 3, 3 comes out first, then 2, then 1. That's exactly how stacks work. It's the same principle here. Now, to be fair, when you're thinking about stacks, they sound like they are just constrained, limited arrays. And honestly, that's exactly what they are. They are simple arrays with a rule around them saying you can only remove the last added item. To be fair, when you do add constraints to things, suddenly you have more power. You can do more things when you have tighter rules around them. Now, think about this, for example. If you had a function call and the function starts running, it says I want a few integers, I want a boolean or 2, then some doubles and some floats, whatever. Each of those are value types, and each of them have to have some sort of storage. It's 8 bytes for an integer, because it's 64-bit, and so forth. And Swift knows ahead of time how much space to give each item. It knows how big an int's going to be, how big a boolean is going to be, or a double, and yada, yada, yada. It knows exactly how big they're going to be. And so rather than going off and asking for 50k of RAM here, 50k of RAM there, whatever, instead, it uses a simple stack pointer. It has its own local bit of memory to work with. And when you say, I want to have an integer, it will subtract from the stack pointer 8 bytes. Say, okay, that bit's your RAM. And you want another one, boom, another 8 bytes come down. That bit's your RAM, and similar. So it allocates RAM very, very quickly and easily. And the best bit is, when it comes to ending the function, we just go, and reset the stack to where it was. Exactly like that. We just push it back up to the top, and we're done. This means it's extremely fast. There's no special magic destroying these objects. Just put the pointer back up to the top of the stack again, and you're done. It'll free up that space for later on. You can just reallocate it to other objects. So it's extremely fast to handle local values and remove them when the function's cleaned up. It'll make sure they're all gone. And that's exactly what happens, by the way. That isn't just a simulated idea. That's exactly how the stack pointer works, handling objects inside functions. Now, like I said, stacks are the easiest type I can think of to work with. So we'll start coding one now. And first, we're going to make some sort of stack struct that is generic over some kind of element, which means we don't want to specify exactly what this stack's going to store. It could be an int, could be strings, could be booleans, whatever. We don't care. It's generic. We want the call site to say, actually, you are a stack of ints. Actually, you're a stack of strings or whatever. So we'll start off really simple. We'll say that we want to have a stack, a struct stack even. And this thing should be generic over element, like that. And you can give this generic type parameter element any name you want. It could be element, it could be T. T is very common. It means nothing special. You can call it elephant if you want to. It means nothing. It's just a name we're providing that will be filled in by whatever is actually used here. It'll be int when we use ints, and string if we use it with strings and so forth. Anyway, inside there, we want to store an array to store our objects, our array of element types. Now remember, these stacks really are just arrays with a limitation, and that is you can only add and remove things at the end. You can't, insert at 0, for example. It's impossible. And so, the great storage here is array. Just use an array and then add constraints in code. So we can say private var array equals an array of what? Well, we already have this element type, so we can say element. Use that for the array type. So it means the underlying array is the same type as our stack. If our stack is a stack of strings, an array is an array of strings. Stack of integers, array is an array of integers, and so forth. Now you'll see I've marked this thing private. We're going to add these rules around our stack. So you can only add things to the end and remove things from the end. If that were public, if we deleted the private var entirely, then folks would just dig into our type and monkey around with the array internally, which is not a good idea. We want to enforce our rules. So I'll say private, you've got to go through our method calls to get to this thing. Now, in terms of actual method calls, there are really only two we care about to begin with. One's called push, for adding items to a stack, and one's called pop, for removing items from a stack. And these just basically wrap the internal array. So we'll say mutating func, push, take some sort of element of type element. Boom. And then we'll just pass it onto our array. Array.append the element. And when it comes to mutating func pop, remove the last element. We'll do returns an optional element and then array.pop last. So it just wraps the array, but it allows us to enforce the rules. They can't do stack.array.insert item 0 or whatever. It's impossible. Now you'll see I've made this pop method return an optional element. So if we are storing ints, like an optional int or strings or whatever, that's simply because it's safer. Like the array might be empty, don't crash the app. But I would totally understand if you wanted to make that a hard crash, but always return element and do a fatal error if there's no items left. You could easily consider that a logic error for programmers trying to pop an empty stack. Don't do that, it's a bad idea. And with that, our basic stack's done, right? We can use it already. We could say, I want to have var numbers, come on Hudson, there we go, equals a stack of ints, and then say numbers.push, 4, then 8, then 15 and 16, whatever you want to. We can add things to the array like that, the stack, sorry. And then we want to remove it, we'll do print numbers.pop. And I'll do it again. So remove the last item from the array multiple times. You see there's a warning over here because this thing returns an optional int. We're converting it to any. That's fine, it'll work out well enough. So it works great. And you could it's generic over whatever you want to. We could have said, var names is a stack of strings. And then names.push Leonardo. Names.push Michelangelo. And names.push Donatello. Question is, am I doing famous artists or Teenage Mutant Ninja Turtles? You'll never know. The point is, it'll hold whatever you want to. Literally hold anything at all, and it'll just pass that type down to the array underneath. It's very, very flexible. So our basic stack works now. That's all the code it takes to get a basic stack up and running. But it's got a few annoyances. Things we can fix to make our stack feel better to use in practice. In fact, there are 5. First, we are missing some valuable external data about our stack. How big is it? How many items does it have? Is it empty or not? Missing that. Second, there is no way of reading the last item without removing it. We've got to call pop and check what it is. We can't say, well, can I just have a preview of what it is? We've got to remove it and then put it back in again. Third, if you have an array that you want to put into your stack, it's very annoying. You've got to make an empty stack and loop over the items in the array and call push each time. It's inefficient. Fourth, if you want to just make a stack simply, here as 1, 2, 3, whatever you want to in a stack, there's no way of doing that. You've got to make an empty stack and push the values by hand again. So that's very annoying as well. And fifth, if you print out numbers, let's do like print numbers here. Oh, come on. Numbers, like that. You'll see it leaks information about our stack. You can see here it's a stack generic of int with an array inside with the values 4, 8, 15, and 16. So it's a bit leaky in terms of you can see the inside array. It's not great. So we're going to fix those things. And fixing them to make them nicer to use is called improving the ergonomics. Lovely phrase. They're actually all very simple to fix. We'll start off by adding count and isEmpty properties. So we'll say var count is an int and returns inside it, just pass it down to the array count. Don't do any fancy work here. Just do array.count. Done. Then there is var isEmpty, a bool. Pass it down to array.isEmpty. .isEmpty. Boom. Done. Nothing else required. Great. That's a first nice step forward. Second, there's no way of seeing what the last item is without having to pop it off and put it on again, which is very annoying. Stacks often have a method just for this purpose. We'll do func peek. And it returns an optional element. And all we'll do is array.last. Send back the last item. Don't remove it, send it back. Done. Third, we can make a dedicated initializer that accepts an existing array into our stack. So rather than to do it by hand, we just say, make a stack from these numbers, please. So we could say up here, init, underscore items, an array of element, self.array equals items. Just copy them in. And that's fine, that'll work, but you'll see an error down here. This code no longer works anymore. That's because we've lost now the default synthesized member-wise initializer for us, for our struct. It's gone. So we want to make that ourselves now. We'll just do init, and then open and close braces. Do no work in there at all, but give us back an empty initializer. We now also have the init items initializer. So we could, if you wanted to, make, let's say, here, var number array is an array of 1, 2, 3, 4, 5, and then var numbers equals stack of number array. Let's pass it in and start working with it, like that. Fourth, we can actually make our stack easier to use, even without arrays, by conforming to a protocol called expressible by array literal. And this allows Swift to assign an array, what looks like an array, directly to a stack with no conversion cost required, which is cool. So to do this, we'll make a new protocol, as a new extension, sorry. Extension on stack conforms to expressible by array literal, this one. It has one required initializer, so if I do init and fill it in, it wants to be element ... here, but otherwise it's good. And I'll do self.array equals elements. That's it. Copy those values in to the array we have internally. It's really nice. Now you don't have to, if you don't want to, put this kind of thing into its own extension. You could put that into the main body of your stack struct. But I do find that in this case, hiving things off by protocol conformance makes it easy to read, which is great. And with that, we can now, like I said, write number arrays simply. It's a much, much nicer way of working. We can go further. We can actually say, I want to make stacks directly from stuff. And we could say, let's say, var numbers is a stack equals 1, 2, 3, 4, 5, like that. And that's what our expressible by array literal does for us. So we now have two ways of making stacks. One was this way, stack from an array, that's the initializer up here. And the other one is expressible by array literal. We can do an array directly like that. And that's not really an array, but it'll be passed in as if it was one, which is great. So it makes our stack easier to make generally, but also with arrays. The last cleanup is not hard code, but it is slightly longer. We want to make our print values down here hide its data, do a custom print value here. And this requires conforming to a protocol called custom debug string convertible. So let's do that now. We'll make our thing conform to that. So we'll say extension stack conforms to custom debug string convertible. And if you think about the algorithm required to make this thing print nicely, we want square bracket 1, 2, 3 square bracket. Just like arrays do, just like sets do in Swift. It's a nice way of working. And to get that, the algorithm for that, exactly what you expect. Make a string with an opening bracket. Then get the first debug value. Then print a comma. Then second debug value, comma, third debug value, end bracket. It's actually surprisingly easy. So to conform to this, we'll say var debug description returns a string. Make our result string be a simple opening bracket. But how we choose to add commas depends whether we are the first element or not. Because the first element has nothing before it, has a square bracket. The second element has a comma before it. Third element, comma before that, but not comma after that. So we'll say var first equals true. We are the first item being parsed. And then for item in array, if we are the first item, then say we are no longer the first item. We've already done first, nothing else required. If we're not the first item, we're going to add to result, comma, space. So we'll do 1, 2, 3, and so forth. Now, the hard part here, the only really hard part, is how we retrieve the debug value for every item in our array. And we can't just use the string form of the item. We can't use print the item. We've got to use a special function here called debug print. And this thing works the same as print, except rather than reading the description, it'll read the debug description. Now it actually takes a parameter here, text output stream, and print takes the same parameter. So nothing special here. It's just that most folks don't recognize print has this, which is obviously a shame. Debug print will say print out our item. I'm going to use terminator of empty string, so don't add a new line after each item. And for the text output stream, I'm going to say ampersand result. Write the change directly to our result. And then after the loop finishes, we're going to say result plus equals an empty bracket to finish it off nicely and return result. Boom. Let's run that back. It builds nicely. Excellent. So now we can go ahead and use that thing. We can say up here, we've got our print values. I'll do print numbers. Hopefully, yeah, exactly like that. 1, 2, 3, 4, 5, 4, 8, 15, 16. So that's the ones we made it with up here, followed by the ones we push on top of it. But it's a custom format now working correctly, which is exactly what we wanted. Much, much nicer to use. Now, there are a variety more protocols we could implement here. We could make this thing conform to more. But the obvious one is sequence, and I wouldn't recommend sequence here. Sequence is something you can loop over, and I can see why you might want that, but that's not how stacks conceptually work. They're not designed to be looped over. We could implement 3 common ones. We could say it's equatable. You could say stack 1 is equal to stack 2. We could say it's hashable. It can go into a set or a dictionary, and it's codable. It can be saved. And if you think about how much code it takes to implement those three protocols, the answer is 4 lines of code, which is remarkable. And it's only 4 rather than 3 because I want to retain some flexibility that I wouldn't otherwise have. And this magic happens because Swift can synthesize conformance to those protocols for us. As long as all the values inside our struct conform to that, it'll be okay. And what actually happens here is our type, our stack type, has an array inside it that has an array of element. And that will conform to element if element conforms to equatable. So it's a chain. Stack will conform to equatable if the array conforms to equatable. An array will conform to equatable if the element conforms to equatable. It'll build up. And it's actually a feature called conditional conformances, introduced in Swift 4.1. It's quite beautiful, and here's how it looks. We could say to our code, real simple, extension stack becomes equatable where element is equatable. That's it. We're saying our struct is equatable if its elements are equatable. That's it. And Swift will synthesize the code for us. It's brilliant. We can now say, let stack A equal the stack of 1, 2, 3. Oops, daisy. 1, 2, 3. And then let stack B be a stack of the array 1, 2, 3. And then print stack A is equal to stack B. And we should get back true. There we go. Boom. So the equatability has worked perfectly thanks to Swift doing it for us. As for hashable, it's exactly the same. I mean, we're going to say extension on stack is hashable, or hashable even, where its elements are also hashable. Boom. It'll do the right thing for us. In fact, only really one of these is interesting, and that is codable. And even then, it's only slightly interesting. Codable is actually a type alias of encodable and decodable. Can be encoded, can be decoded. Together make codable, the sort of super protocol, as it were. And we can totally make this conform to codable. We could say extension stack conforms to codable where element conforms to codable. You can do that. Of course you can. But we're restricting what we can do. You know, if you have an item that is encodable but not decodable, it can't go into our stack. This thing means it'll conform to both encodable and decodable if its elements conform to encodable and decodable, which is not very nice. It's better to write this as extension stack conforms to decodable where element is decodable. Like that, decodable. Same again for encodable down here. En. And that actually looks the same, but gives us some bonus flexibility. We can now have items that are only encodable, only decodable, whatever you want to. And that's it. Like with just 4 lines of code, equatable, hashable, decodable, and encodable were written live on stage. Hopefully you can see how useful this stuff is, either conceptually for knowing how data structures work, or in practice for actually using a real struct in action. But we covered a lot. We've covered conditional conformances, making our stack more flexible, wrapping types and so forth. There's been a lot going on, but I hope it was useful.